Good morning, sir. My name is Mohammed Zamira. My phone number is 21951804A1. I am from EC Department B section. My topic is test of logic DNA systems. Engineering DNA logic system is considered as one of the most promising strategies for next generation molecular computers owing to the inherent features of DNA such as low cost, easy synthesis, controllable hybridization. Various DNA logic devices with different functions have been developed in the recent decades. Besides a variety of logical programmed biological applications are also explored, which initiates a new chapter of DNA logic computing. Although these fields has gained rapid developments, a statistical review that could not only elaborate logic principles of diverse DNA logic devices but also outline decent representative works is urgently needed. This review we of course elaborate the general classifications, the logic principles of diverse DNA logic devices in which the operating strategies of these devices and representations examples are selectively presented. Then we review state of the art advancements of DNA computing based on the different non-canonical DNA on nanostructures during the past decade in which some classical works are summarized. After that, the innovations applications of DNA computing to logic controlled bioanalysis, cells imaging and drug growth. Finally, we analyze current obstacles and suggest approximate prospects for this area. DNA computing is an advancing branch of unconventional computing, which are DNA biochemistry and molecular biological hardware. Instead of traditional electronic computing, research and development in this area concerns theory, experiments, and applications. Now being expanded to several other avenues such as development of storage technologies, nanoscales, imagines modalities, synthetic controllers, and reactions networks, etc. Non-canonical DNA structures. History. Leonard Allender of the University of Southern California initially developed this field in 1994. Aldevin demonstrated a proof of concepts use of DNA as a form of computations which solved the 7-point Hamiltonian path problems. Since the initial Aldevin experiments, advances have occurred and various Turing machines have been proven by unconstable. Since the field has expanded into several avenues, DNA computing into the development of memory technologies, all the field DNA computing can be categorized as a subfield. DNA Nansen field started by the river. It morphed into the field of structured DNA self-assembled, which has the 2020 is extremely meters in size have been demonstrated in 2018. In 1994, Prof. Siemens group demonstrated early DNA lattice structures using a small set of DNA components. In 2003, Raphael's DNA grow exponentials related for computer science and biochemists started exploring tile assembly, arbitrary computations upon growth. Other avenues that were theoretically explored in the late 90s, including DNA-based security and cryptography, computational capacity of DNA systems, DNA memories, and disk and DNA-based properties. In 2003, Reeves group first demonstrated the idea of DNA-based walker that traversed along a track similar to a line-followed robot. They used molecular biology as a source of energy for the walker. Since these first demonstrations, a wide variety of DNA-based walker have been demonstrated. Applications, examples, and recent developments. In 1994, Leonard Allman presented the first prototype of DNA computers. The TTF-100 was a test tube filled with 100 microliters of DNA solutions. He managed to solve an instant of direct Hamilton path problem. DNA fragments are created, each of them representing city that have to visit, and every one of the fragments is capable of linkage with other fragments created. These DNA fragments were produced and mixed in a test tube within seconds. The small fragments are the bigger ones representing the different travels routes through a chemical reactions. The DNA fragments representing the longer routes were eliminated. The remains are the solutions to the problem, but all over the experiment lasted a week. However, current technical limitations prevent the evolutions of the research. Therefore, the experiments isn't suitable for the applications, but it is a nevertheless a proof of concept tic-tac-toe game, but default the computer is considered to have a plate first in the central square. The player starts with the 8 different types of DNA stands corresponding to the 8 remaining boxes that may be played to play box number if the human players was in all bins. Stands corresponding to the input. The stands bin to certain DNA enzymes, which binds to the substrate and cuts. The corresponding bin becomes fluorescent, indicates which box is being played to the DNA computers. The DNA enzymes are divided among the bins in such a way as to ensure the best the human player can achieve is draw as real tic-tac-toe. Renewable DNA computing system. Subsequent research of DNA computing has produced reverse DNA computing, bringing the technology one step closer to the silicon-based computers used. These, in particular, John Relief and these group Duke University have proposed to do different techniques to reuse the computing DNA complexes. The first design uses DNA gates, with the second uses DNA hairpins complexes. Synthesis strategies, reversible circuits of DNA computers, papers, implementations, reversible gates and circuiting of DNA computers by combining DNA computing and reversible computing techniques. This paper also proposes a universal reversible gate library for synthesizing and reversible circuits on DNA computers with an average length and cost of constructed circuits DNA between the previous methods. There are multiple methods for building a computing device based on DNA with its own advantage and disadvantage. Both of these builds the basic logics and are not associated with the logic for a DNA basis. Some of different bases include enzyme stand displacements mechanisms, the most fundamental operations in DNA computing and molecular programming. In strand displacements mechanism, currently there are two ways to perform strand displacements: two hole mediated strand displacements, monomers based strand displacements, two hole exchange. Besides simple strands displacement schemes, DNA computers have also been constructed using the concept of two-hole exchange in the systems and input DNA strands behind a stick end. This allows the creations of modular logic components such as AND, OR, and NOT gates and single amplifiers, which can be linked into arbitrary large computers. This class of DNA computers does not require enzymes and chemical capability of the DNA. Chemical reactions networks. The full stack of DNA computing looks very similar to a traditional computing architecture. At the highest level, see like general purpose problem representing gets translated to domain level DNA design and implemented using a set of DNA standards. In 2010 showed that DNA can be used to subtract the implementation arbitrary chemical reactions. This opened the way to design and synthesis of the biochemical controllers, since the expressive power of cRNAs is equivalent to the turning machines. Such controllers can potentially be used in vivo applications such as preventing hormone imbalance, enzymes. DNA enzymes logic gates changes its structures when it binds to a matching oligomer and the fluoro substrate. It is bonded to a cleaved free, while other materials can be used. Most models uses a fluorescent based substrate because it is very easy to detect even at the single molecular limit. The amount of fluorescent can then be measured to the well or not reactions took place. The enzymes that changes is then used and cannot initiate any more reactions. Because of this, these reactions takes place in a device such as continuous stick tank reactors, where old product is removed and new molecules added. Two commonly used DNA enzymes are named. These are popular because they allow cleaving of a substrate in an arbitrary locations. A design called stem loop consisting of a single strand of DNA which has a loop at an end or a dynamic construct that opens and closes which a piece of DNA bonds to the loop part. Enzymes based on DNA computers are usually of the form of simple turning machines. There is analogous hardware in the form of and enzymes and software in the form of DNA. Expanded on their work by work going to the show automatic diagnosis. Our limitations of implementation is that two separate automata are required. One to the administrator each of the entire process of evolutions until drug releases took around an hour to complete. This method also requires the transmission molecules as well as the Falk enzymes to the presently required the Falk enzymes. It should also be pointed out that the software molecules can be reused in cases. Algorithm self-assembled DNA nanotechnology has been applied to the related field of DNA computing. DNA tiles can be designed to contain multiple sticky and in the sequence chosen so that they act as a Wang tile. XOR operations this allows the DNA arrays to implement a cellular automations which generates a fact called the strings or DNA arrays, increasing its scope beyond simple periodic arrays. Capability DNA computing is a form of parallel computing in that it takes advantages of many different molecules of DNA to try many different possibilities at once. For certain specialized problems, DNA computers are faster and smaller than any other computers built so far. Furthermore, particular mathematical computations have been demonstrated to work on a DNA computers. DNA computing does not provide any new capabilities from the standpoints of computability theory, the study of which problems are computational solvable using different modules of computations for exponentials with the size of problems on non-neon machines. It shows those exponentials with the size of problems of DNA machines. For very large expensive problems, the amount of DNA required is too large to practicals. Neural network based computing. Kevin Cherry program of a computer in advance with appropriate set of weights represented by varying concentrations weight molecules which will be later added to the test tube that holds the impure DNA strands. Pros and cons. The slow processing speed of DNA computers is compensated in potentials to make high amount of parallel computations. This is achieved by the fact that millions of billions molecules interact with each other simultaneously. However, it is much harder to analyze the answers by giving by a DNA computer than a digital one. Thank you for giving me this wonderful opportunity.